Okay, so I'll share my screen. So this is the notes that I've sent out to you. Can you see them?
Yep.
Yep.
Okay, hi Stephen, how are you?
Hey, doing good.
Good, thanks for attending. We're just going to start now because it's already a couple of minutes past. So I've issued the notes. This first part, the cooling cycle, from the indoor and rejected to the outdoor. I've given a description of the processes there, but I'm just going to, I'm not going to read all that out. I'm just going to put the schematic up and we'll have a quick look at this, which is a good one. And I sent this out as well. So in the cooling process, the indoor coil, what's commonly called the evaporator, absorbs heat from the inside. The evaporator fan obviously blows the air through the coil or draws the air through the coil and delivers it to the space. And so the liquid refrigerant turns into a gas, a low pressure, low temperature gas. That's called the suction line. And you'll see this commonly referred to in the documentation on equipment. So the suction line is usually a bigger pipe than the liquid line because you've turned it into a gas. You need a bigger volume to carry the vapour. That's drawn into the compressor through the reversing valve, and it's compressed into a high pressure, high temperature gas or vapour. And that line then carries it through to the condenser. And the line is called a discharge line or a hot gas line. Okay, it goes, so that's a hot pipe. It goes to the condenser, and the condenser then rejects the heat to the outside with the help of the condenser fan. Or an outdoor coil, condenser is a common terminology. And that turns the refrigerant into a liquid. So then the liquid line comes back towards the evaporator. It goes through an expansion device, which is normally housed in the fan coil unit. It's not out in the field. If it's a big refrigeration system, it would be all separate components. But in this case, any expansion device would be inside the fan coil unit. When it goes through the expansion valve, it turns into a low pressure, low temperature liquid and goes back into the evaporator, and the process continues. One thing I was going to say over here is the compressor and condenser and the reversing valve are normally enclosed in the condensing unit, which is the outside unit. So the unit outside little package has got all that in it, compressor and condenser. And the fan coil unit inside has obviously got the fan, the coil, and any expansion devices. Go back to the notes. So that's the cooling cycle. The reversing valve changes the refrigeration cycle from cooling to heating when it's commanded by the space temperature control. So that could be automatic, it might be manual, depending on the system. If it's automatic, it automatically changes over. The reversing valve goes to heating. And the refrigerant flows in the opposite direction. The indoor coil now provides heating to the space, and the outdoor coil extracts heat from the outside to be transferred indoors via the refrigerant. So even though it's cold, it can be cold outside and even down below zero, the refrigerant can still extract heat from the outside and bring it inside. The thermal energy efficiency of the system is higher in heating mode because the heat generated by the compressor motor is also absorbed by the refrigerant and delivered to the indoor coil. So you basically get more heating capacity for each unit of power input. So back to the schematic, we'll go to the heating cycle. So let's go to the inside coil again. This time, this coil becomes the condenser, and that's releasing heat to the inside with the help of the fan. And the flow of refrigerant is this way. So this is now the condenser. It's just the exact opposite to what's in the cooling cycle. So we've now got this liquid line coming out of the indoor coil through an expansion device into the outside coil, which is now the evaporator. And that absorbs heat from the air, from the outside air, to bring it back inside. So the coming out of the evaporator in this case, or the outdoor coil, we've got a low pressure, low temperature vapor, which goes through the reversing valve to the compressor, compressed to a high pressure, high temperature vapor, back to the indoor coil. And remember that in the compressor there, it's the compressor motor heat is also getting into the refrigerant. The refrigerant cools the motor and delivers that inside. So it's, I think in that schematic, it describes that quite succinctly. And that's probably a good one to have handy if you're ever wondering how it works. Okay, back to the notes. Now, terminology in the HVAC business, as you would have already seen, there's lots of abbreviations for lots of different things. So you've got to get used to this because people talk in abbreviations. It saves a lot of time writing things out. So an FCU is a fan coil unit. It's got the indoor coil, fan, filter, and controls. The CU is normally the normal description for a condensing unit, which is the outdoor unit, which has got the outdoor coil, fan, compressor, reversing valve, and controls. PAC, packaged air conditioner, that's a complete system comprising the fan coil unit, condensing unit, compressor, and controls all in one casing. VRF, variable refrigerant flow, multiple fan coil units connected to one or more condensing units. VRV is variable refrigerant volume, but it's the same as a VRF. VRV is a Daikin proprietary brand. I think Daikin might have been the inventors of this system originally. I couldn't be sure of that, but I'm pretty sure Daikin came up with VRV, and then the other competitors followed and they called it VRF to be different because they couldn't call it VRV because Daikin obviously had a patent on that brand. Excuse me. So I guess a lot of you've already seen all this stuff, but I wanted to go through it anyway. It's just going to the basics, and we've only got the three of you attending at the moment, but some of you may not have even come across some of these things yet, so this is why I'm going through it. Non-ducted split systems, air-cooled. In this case, we've got a fan coil unit, indoor fan coil unit, and outdoor condensing unit connected by refrigerant pipework. Fan coil units are exposed to view, and conditioned air is delivered directly from the fan coil unit to the indoor space. So I've got a picture here of typical sorts of things. This is a Mitsubishi brochure that I grabbed just to have a look at. So these are the wall-mounted fan coil units. You can get ceiling-mounted cassettes or under-ceiling units for high capacity. So you've all seen those. You've probably got them at home. Now, a couple of things to be aware of. The condensing unit is installed outside normally and should be outside the building in an open space to allow unrestricted airflow to the outdoor coil, in this case an air-cooled condenser. This is really important. Sometimes someone in the project team, such as an architect, might try and hide the condensing units so that nobody can see them. Be very careful of that, because if you put it inside an enclosure, they're not going to work properly, and the system just won't function. So if it does have to go in an enclosure, make sure you've got decent louvers to let the air come in and out of that enclosure. Now, DX split systems are limited in the allowable length of refrigerant pipe between the fan coil unit and condensing unit. This is another one to be aware of. Typically, for small systems, the maximum length of pipe is probably about 15 metres. You might be able to get up to 30 metres of pipe, but make sure you look at the manufacturer's literature on the system you're looking at to see what length of pipe you can have. Because if you go over that, you're going to lose performance. And as I said before, various types of indoor fan coil units are available. Ducted split systems, basically the same, but this time the indoor unit is ducted. The fan coil unit and condensing unit connected by pipework, refrigerant pipework. Fan coil units are normally concealed from view above the ceiling or in a plant room or some other remote space. And the condensing unit's outside. Again, make sure you've got unrestricted airflow to the condenser. And these are limited in the length of refrigerant pipe allowable as well. So basically the same thing. Refer to the literature to see how much pipe work you can have. So in this case, the conditioned air is delivered from the fan coil unit to air outlets in the indoor space through insulated rigid and flexible duct. Return air duct is required. Outside air ductwork may also be required. Now, I mentioned draw through or blow through here. I'll show you a picture of a ducted unit. Again, I've just taken this from Mitsubishi catalogue. That's a typical ducted fan coil unit for a DX system. It's got dual fans here. There's centrifugal fans. Typically, these, what capacity is that one? That's 10 to 14 kilowatts. This one is 5 to 14. This is a slimline one for even tighter spaces. So the coil, these units are generally wider because you still need to get a large coil area to get the cooling capacity or heating capacity. But these units are typically blow through. So here's the fans. This is where the return air comes back into the unit here, goes through the fans, and you can see the pipes over here. The air is going in that direction. So that's called a blow-through unit, where the air is blowing through the coil. The draw-through is where the air is drawn through the coil, which is more common in the bigger fan coil units and air handling units. Okay, ductwork and filters and other components in the ductwork impose airflow resistance on the fan coil unit supply air fan. So the fan has to be capable of circulating the required supply air and return air against the calculated static pressure of the duct system and filters. So you work out the static pressure and then select the unit to make sure the fan can achieve that static pressure. I'm sure you're all aware of that. That's really basic, fundamental, and very important. Fan coil units are usually horizontal configuration. The ones we just looked at are horizontal type, and that means the air flows through the units in a horizontal direction. This provides the lowest profile, and I'm sure you've all come across this situation over and time and again, where there's very limited space to put these units above the ceiling. So that's why there are low profile units if you really push for space. You can get vertical units if the project requires it, so they might be installed in a cupboard or something like that. Okay, package systems. Firstly, air-cooled. In this case, the fan coil unit, condensing unit, and all the components are enclosed in a single package, in a weatherproof enclosure or package. In this case, all of the refrigerant pipework is installed in the factory inside the package, so there's no pipework required. They're normally installed on a roof or on the ground outside in an open space, again to allow unrestricted airflow to the outdoor coil. Again, you've got ductwork delivering the conditioned air to the space through outlets, through insulated rigid and flexible duct. Return air ductwork is required. Outside air ductwork may be required Generally, the outside air duct is just a short branch above the roof with the damper on it. Excuse me. These usually draw through. So I've got a picture of, this is a temper zone unit. In this case, you can see the fan scrolls. They're forward curve centrifugal fans. This is the return air spigot here. So return air comes through here. On the front of that spigot, you'd have a plenum with filters in it. Goes through the cooling coil and then comes back out through the fan, through the supply air fan, out to the space. And you've got a cooling coil just inside there, cooling the heating coil. On top here is the condenser fan. This is only a small unit, so it's only got the one fan. As they get bigger, you'll have more and more condenser fans to handle the volume of air required. In this case, the condenser coil, you can't see it, but would be on the back of the unit. So the condenser air comes through up to the fan and then discharges vertically out of there. So once again, you've got to work out the static pressure of the fan and make sure the fan is selected to cope with that. Now these package units, the temper zone units, are available with EC fans. We're going to talk about this a bit later on in another session, but you can have a standard centrifugal fan, or you can get EC fans as well. DC fans, well, you've probably come across them already. They're speed controllable. EC means electronic commutator. So they can be controlled externally if you want to, or internally through the package unit, and they provide some energy efficiency. Now you can also get water-cooled package units, but in this case you require a cooling tower or a forced draft cooler, water pipe work, pumps and controls. So there's a lot more equipment involved. Water-cooled systems generally offer improved energy efficiency compared with air-cooled, but there's a higher capital and maintenance cost. They're best suited to projects where air-cooled condensers are impractical. So if you can't put a number of air-cooled condensers outside the building, which is quite common in a multi-storey building, so water-cooled can be beneficial. If there's insufficient space for the condensers outside, refrigerant pipes are too long. So in this case, with water-cooled, you're running water pipe, and with a pump, you've sort of got unlimited length of pipe that you can push the water through. Or if it's not possible or practical to run ductwork from the air-cooled package unit through the building. So air-cooled package units are probably more suitable to single-storey buildings, where you can put the equipment on the roof, come down through the roof, and then the ductwork runs through the ceiling space. I've got a picture of a water-cooled one. This is a temper zone one again. And these units are a bit taller, a bit higher than the air-cooled ones tend to be, but you can put these in the ceiling space. So this unit has got the fan coil unit. There's the fan coil unit supply fan there. In this case, though, you've got a water-cooled condenser. So you can see a couple of pipe stubs there. That's where the condenser water comes in. So it's a package unit. Everything's in there, but the water has to go off to a cooling tower or fluid cooler, which will be located outside. So that's another option. Just beware with these that because they have a compressor in them, they make a bit more noise than an air-cooled unit. So just be careful of acoustics. Okay, now let's move on to VRF. Or any questions so far? Just wave your head or shake your head if you've got any questions. No? Okay.
I had a
VRF.
question. Sorry.
Yep.
Wait,
Right.
so you wrote down that the water-cooled systems are advantageous because like you might have a situation where there's not enough space for air-cooled condensers outside the building. But
Yep.
if you don't have space for air-cooled condensers on the outside of the building, why would you have space for cooling towers instead?
Well, it depends on the size of the building, and the space made available for condensers. So there's a few reasons why you might use a water-cooled system. They are more energy efficient, but you're going to have a roof over the building, and sometimes you've only got a very small space on the roof of the building available for plant. So in that case, you might be able to fit a cooling tower in that small space, but you won't be able to fit a whole lot of air-cooled condensers.
Oh, because you would need like sufficient spacing between multiple condensers. Is that why?
Yeah, and that's right. And it depends the type of system you have. Like if you're doing individual split systems, you'll have a condenser for every fan coil unit. But now we're going to talk about VRF or VRV systems where you can have multiple fan coil units, but only one or 1 to 3 or 4 condensing units, and so they become more compact. Okay, so that's the benefit of the VRF. So does that answer your question?
Yep, thanks.
I mean, there are a number of reasons why you might choose to go that way. One job that comes to mind for some reason was done a long time ago. I was involved in it. Was a university building, and they wanted to have individual control in every classroom, every workspace within this new building at the university. In those days, actually, VRF didn't even exist. Okay, so the only option we really had was to go with either a chilled water system and have chillers and probably a water boiler, obviously cooling tower. We could have used an air-cooled chiller on the roof, but the university decided that they were happy with having water-cooled package units in each space and then putting a cooling tower outside. Now, I can't remember where we put the cooling tower. It might have been on the ground because universities, have a bit of open space available. But generally, they tend to go on the roof. So there's a number of reasons. And in the short time we've got here, I can't go through everything, but you'll see as you go through what's most appropriate, I guess, for the project you're working on. Okay, you're right with it?
I'm sorry, just one more question. Is it also easier to plug into a cooling tower as opposed to installing a whole new like VRF system for an existing building?
Potentially, yes. There's another job that I was involved with, which was an apartment building, and every apartment obviously is an individual owner's property. So it was about a 10-story building, and in that case, once again, this is an oldish building, so VRF wasn't available when it was built. So they decided the best way to go was to have a cooling tower on the roof and water-cooled package units in each apartment. And so then you can duct to different rooms throughout each apartment. And because it's water is easier to transport than refrigerant pipe or refrigerant. So, there's any number of different options you can use. And now with VRF, it makes it a bit easier because you've got a bit more flexibility in the design of the system. So, you right with that, John?
Yeah, thanks.
Yeah. So let's have a look at VRF systems. So far we've talked about non-ducted and ducted DX split systems being standalone. So one fan coil unit to one condenser. But you can have multiple fan coil units connected to only one condensing unit. The most common way of combining multiple fan coil units with one condensing unit is by using a VRF or VRV system. Therefore, the VRF systems are basically multiple split systems utilising only one or possibly more common condensers. The number of condensers obviously depends on the system capacity. And you'll find when you look at the data that, I haven't looked at it recently, but it used to be something like, I think you can go up to about 200 kilowatts with one condenser. And then you guys have probably looked at it yourselves. If you've got more than that capacity required, then you probably need at least another condenser. And you used to be able to go up to about 1,000 kilowatts. It's not a very good schematic, but this shows there's 3 condensing units there and multiple indoor fan coil units. In this case, it's just a 2-pipe system, a liquid pipe, and they call it gas pipe. That's the suction pipe that we were talking about before, where the gas is taken back to the compressor. And when you purchase these systems, the suppliers provide you with all the necessary pipe fittings to make these connections. Got another schematic here, which is a bit clearer. In this case, there's 4 condensing units here, and various types of indoor units. So there's under ceiling cassettes, wall mounted fan coil units, ducted units, and so on. So they're very versatile, and they've got some other benefits too. So back to the notes. VRF condensing units can be air-cooled or water-cooled, depending on the type of project and the budget. Water-cooled VRF condensing units have the advantage of being suitable for installation inside the building in a cupboard or a plant room, and that's quite common to do that. So once again, you're talking about a comparison between trying to, if you've got a very big building and you have a lot of condensing units required, then you've got to run, if it's an air-cooled system, you've got to run refrigerant pipework through the building up to the roof, and then arrange all your air-cooled condensing units on the roof somewhere. So that can be difficult to find the space. So there is a water-cooled option where you can put the condensing unit inside the building in a cup, and then the pipework between the condensing unit and the heat rejection is water pipe. So you're going to a cooling tower or a fluid cooler on the roof. The fan coil units used in a VRF system are similar to the standalone fan coil units, but the piping and controls are different to enable connection to the VRF system. VRF fan coil units are the same for air-cooled and water-cooled systems. So exactly the same fan coil units, but you just either have an air-cooled condensing unit or a water-cooled one. Another advantage of VRF systems is that you can have relatively long runs of refrigerant pipe. Once again, you need to refer to the manufacturer's data because there's a certain length you can have from the fan coil unit to a branch pipe, and then from the branch pipe to the next branch, and then from there to the condenser and so on. So that they usually give you diagrams so you can work out what you can have, but overall you can have a huge amount of pipe work involved in a VRF system, refrigerant pipe. It's important to be aware of potential leakage of refrigerant into occupied spaces if there's a fault in the system somewhere, like a faulty joint or a damaged pipe or something, faulty coil. So if you've got a VRF system with lots of fan coil units in a space with lots of rooms, and you've got, say, a fan coil unit in each room, there's potential for, if there's a fault in the system, that any particular room, the refrigerant of the whole system might leak into one room. It's unlikely, but it can happen. And refrigerants are generally heavier than air, and they're asphyxiants, which means they take your breath away. meaning exposure to the refrigerant can cause breathing problems and can be potentially fatal. So if it's leaking into a space and you're not aware of it, and I've noted there, particularly in residential buildings, like an aged care building, if someone's in bed and there's a fault with the VRF system or a leak of refrigerant, somebody could be sleeping in bed and the room is filling up with refrigerant. So that person, unfortunately, may not wake up because they can't breathe. The refrigerant replaces the air in the room. So this is an issue that you need to be aware of and you need to deal with when you have a distributed system. So you need to calculate the potential refrigerant concentration in the case of leakage in each space. If the concentration exceeds the allowable limit in each space, then, or any space, then remedial measures must be taken to relieve or remove the refrigerant for the safety of the occupants. Now, this has got to be something that happens automatically, preferably so that you don't need action. I've listed down a few possible remedial actions, but AS 5194 is the Australian standard that covers these things. So you need to have a look at that. But some possible actions might include relieving the refrigerant to an adjacent space, such as a low-level door grill. So as long as the adjacent space is large enough to take the volume of the system, you can relieve it to a bigger space and it's not going to cause a problem. But to do that, obviously, you've got to be able to put a door grill in there, and that may not always be feasible. In the case of an aged care building, they probably don't want door grills indoors because they're private rooms and they want their privacy. So that may not be feasible. You could have low-level exhaust grills in the space. Now you can connect it to an exhaust system, so it runs all the time. But that may not be acceptable to an architect, or it might not suit the space. You can have refrigerant concentration alarms. Now, I have done this, but mostly in a more industrial project where they had distributed system, VRF system, and they just said, just put alarms in. But they're expensive. If the concentration is a bit high, the alarm goes off and people know that they have to evacuate the space if that happens. It's an option. Now, the other option is you can use more condensing units to reduce the amount of refrigerant in each system. Okay, so instead of having one large one, let's say it's 100 kilowatts, maybe you could go to two smaller ones of 50 kilowatts each and break it up so that you're reducing the amount of refrigerant in the system. The VRF systems can be heat pump type or heat recovery type. Typical suppliers, Daikin, Mitsubishi, Fujitsu, there's a few others as well, as you're probably well aware. The heat pump VRF system, in this one, all of the fan coil units operate only in the mode selected at the controller. So it's either cooling or heating, but not both at the same time. So it's important to group the fan coil units and the VRF condensing unit to ensure that this arrangement will not cause any space temperature problems. Because if you select cooling at any one of the fan coil units, everything gets cooling. Right? So, for example, it's normally not satisfactory to group internal and perimeter zone fan coil units with one common condensing unit, as a perimeter zone might require heating when an internal zone might require cooling. So if the internal zone switches to cooling, and it's usually, it may have changed, but when I was doing these, it's basically a master-slave arrangement, which means the first one to turn on is the master. Okay, so if someone turns a unit on in the center zone and they want cooling, the whole system gets cooling. So you've got to group them so that they've got this similar sort of load profile. The same thing occurs if you've got general office space and meeting rooms. If you've got a meeting room where a lot of people go at one time and it gets very hot in there because they're in there for an hour or two, if they want cooling, but the general office doesn't need the cooling, the meeting room may not get it, or vice versa. The meeting room wants cooling, but the office doesn't. So just group them together so it's they're in the same thermal zone. Heat pump VRF systems are typically two-pipe, which is liquid and suction, as we said before. The pipe work will have special fittings installed to enable satisfactory flow of refrigerant to all fan coil units. So that's what we looked at before in that schematic. The heat recovery VRF. The fan coil units can operate independently and simultaneously in either cooling or heating mode with a common condenser. This system provides improved energy efficiency because the heat removed from one zone requiring cooling can be transferred by the VRF system to another zone which requires heating. So this is a good system, very efficient. In this case, it's possible and beneficial to group internal and perimeter zone fan coil units with one common condensing unit. So now it doesn't matter. You can connect whatever you like to it now, and it's beneficial to do that. You can get two-pipe systems or three-pipe systems, depending on the manufacturer. Now, I don't know whether you're aware, but Mitsubishi have a two-pipe heat recovery VRF system. I don't think anyone else does. Well, they never used to. And Daikin is a three-pipe. I think the others are three-pipe. I think Mitsubishi's got a patent on the two-pipe system. But the two-pipe systems also require additional field devices, a big box with pipes connected to it, so you can get the heat process working, the heat recovery process working. Excuse me. Heat recovery VRF systems are more complex than heat pump systems, and therefore more expensive. There's more pipe work involved, particularly if it's a three-pipe system. And the additional capital cost may be offset in time by the energy savings achievable. So if you're looking at a heat recovery system, there will be a higher cost, but you might be able to justify that by saying that there will be energy savings. You can calculate the energy savings and see how long it's going to take to pay that off, pay the investment back. So when you're talking about VRF systems, and we'll get onto this later, we're going to talk about chilled water and heating water systems a bit later on in the sessions. VRF is kind of the DX equivalent of a chilled water system. So we'll talk about that in more detail later. And it's probably overall a bit less expensive than chilled water, but that may have changed. I just want to mention condensate drains. Cooling coils reduce the temperature of the air passing through the coil and also remove, oh, sorry, before I go on, any questions on VRF or VRV? All good? Okay. Condensate drains. So when you're reducing the air passing through the coil, you're also dehumidifying the air and removing moisture. So this applies to indoor coils in cooling mode and outdoor coils in the heating mode. Moisture condenses into water and must be drained away from the fan coil unit or condensing unit to a suitable drainage point. Condensate drain pipes need to fall in the direction of flow, otherwise they'll tend to cause water leakage in the building. So when you're doing your layouts with fan coil units, I'm sure you've all done this, always be aware that you've got to get the condensate out of the building somehow. You know, one option might be to get the hydraulics contractor, the plumbers, to give you a tundish adjacent to the fan coil unit. Then it takes away your concerns about trying to run a condensate pipe out of the building. With tight ceiling spaces, it makes it very difficult because you want to try and get the fan coil unit up as high as you can so that you've got enough space in the ceiling to run a condensate drain to the nearest drain point. So be aware of that, because if you have water leaks in the building, you've got a big problem. The condensate drain lines must have an open discharge point to ensure that the condensate is flowing correctly and avoid cross-contamination. Condensate trap is required in the fan coil unit drain pipe to avoid negative air pressure, preventing the flow of condensate. What I mean by that is the condensate pipe is connected to the drain pan underneath the cooling coil, and the air is being drawn over through the cooling coil or blown through it. If it's being drawn through, you're creating a negative pressure. If you don't have a water trap in the pipe, then the water won't flow. So you're going to cause a problem there. It will overflow out of the drain, out of the drain pan. If you've got a blow-through system, you're putting pressure onto the pipe and trying to force air through the pipe. And if you don't have a trap, you're losing conditioned air straight out through the pipe. So I'll just show you a picture of one. This is obviously an outside unit, but there's the trap there. That trap has to be equal to or greater than the static pressure of the fan, and it's full of water. Okay. So when the water is draining out of the drain pan, come down here and just as the level goes up, it drains out. In this case, it just drops on the ground. Some local governments have requirements about what you can do with condensate drains or where you can discharge them. So you need to be aware of that and check with the local authorities to see what they'll accept. Basically, it's clean water, but sometimes they have requirements about where you can discharge it. Some suitable points for draining might be a tundish adjacent or close to the fan coil unit. That's ideal, because then the worry of getting the water out is not your problem anymore. It's the hydraulics contractor who has to find a drain for it. We might be able to get outside the building to a garden area or something like that. Or you might be able to get a tundish. You might be able to go to a kitchen area and get a tundish in a kitchen or something where you can drain to. Now, filters. All air conditioning systems must have filters to remove airborne dust and particulates. The filters are normally installed in a return / outside airstream upstream of the cooling or heating coil. This location is chosen because it prevents the dust and particulates from settling on the coil and affecting the heat transfer efficiency. So it's not easy to clean a coil. Well, depending on the system, if it's an air handling unit, you can get inside and clean it out. But for small fan coil units, it's very difficult to clean a coil. So you want a filter there to catch everything before it gets to the coil. And also because coils get wet from condensation, any dust and particulates that gather on the coils can become a bacterial growth potential. And then you've got mold growing on the coil or inside the ductwork, which can get inside. So you want to get the dust out before it gets to the coil. Filters come in a wide range of forms, sizes, filter media options, and so on. In this case, we're just talking about fan coil units and package units. There are lots of other different filters for different applications, such as in a hospital. You might have HEPA filters, but we won't talk about those at this stage. For a non-ducted split system, such as a wall-mounted fan coil unit, they come with proprietary filters. So you don't need to provide any additional filters there. And they can be removed and cleaned. Ducted split systems, including VRF, typically are panel filters. They can have thicknesses of 25 mil, 50 or 100, or even less than 25, but 25 is probably the usual minimum. The filter media can be washable or disposable, and the filters are normally installed in a plenum attached to the return air connection of the fan coil unit. So got a photo here of a typical panel filter. This is from Email Air Handling, Australian company. This is good data. If you're looking for data on filters, AES Environmental handle the email filters now. And this gives you good data on the different grades available and the different thicknesses. So 25, you can have G4, 50, you can have G4 or F5, and 100 mil, same, G4 or F5. And it gives you clean pressure drops for different airflows. Depending on the size, the pressure drop over on the right-hand side for high capacity is normally rated at 2.5 meters a second face velocity. So if your face velocity is less than that, your pressure drop will be lower. So that's important in your fan static calculations to know what the right or correct pressure drop is when it's clean, so you can do your calcs. In a packaged unit, because they're outside the building, there's a much higher airflow, you typically use deep bed filters. There's more space available to fit the filters in. These take up obviously a lot more room, but you'll need a lot more filters because there'll be a lot more air flowing. The filter media is normally disposable, and they're installed in a plate attached to the package unit opening. So there's once again, email air handling, typical sort of deep bed filter. And again, you've got all the data there. So in this case, the ratings for these, F6, F7, F8, F9. I think you can get an F5. It's not shown on this particular brochure, but mostly the F5 is not used in deep bed filters anymore, so they're going to the higher ratings. So, but the higher ratings obviously have higher pressure drops as well. So filter ratings for fan core units are normally G4 or F5, as we saw there. And filter ratings for package units are normally required to be rated F5 or above. As filter media ratings increase, what that means, the ratings relate to the dust arrestance efficiency. Okay, well, have a look at a comparison chart in a second. As the ratings increase, the airflow resistance or pressure drop also increases, and air pressure drop is also a function of face velocity, which I mentioned before. So you never want to go over 2.5 meters a second if you can avoid it. And but they take up a lot of space as well. So if you can, and sometimes a design brief will require a lower face velocity, say 1.8 or 1.5, which is reducing the pressure drop, but it's increasing the space required to fit the filters in. And now in the Air Technical Handbook, this is the 5th edition, page 175. This gives a comparison between filter ratings. Sometimes if you look at a filter supplier's data, they might say it's an M6. What does that mean? Well, these on the left-hand side is the Australian ratings from G1 to G4, F5 to F9. This gives the average efficiency on test dust number 1. And normally you can't use anything less than G4. Because G4, if you go over to the right-hand side here, it's got an ASHRAE rating of 20 to 30%. And as the ratings go up, the efficiency improves. But so does the pressure drop, obviously. So as you're going up this scale, the pressure drop increases a lot. This column, EN779, these are the European ratings. Sometimes they'll say they want an M5 filter. What's that? In our language, it's an F5, okay? So this is handy just to compare those. And then in the US, they talk in MERV, which means, I'm trying to think of it. Can't think what that stands for, but you can find that out if you want to. So these are the different ratings, and this is a good chart to say, if they've asked for a MERV 9 to 10, what does that mean to us in Australia? Right. Any questions on filters? Okay. Refrigerants. I've just listed there some refrigerants here that just for interest. There's a wealth of information available online if you want to look up refrigerants. These are the most common ones. So the refrigerants used to transfer the heat around the cycle. During the cycle, the refrigerant changes phases between liquid and gas, as we discussed earlier. Refrigerants are regulated due to toxicity, flammability, pressure, temperature, and contribution to the ozone depletion and greenhouse gases. And most of them are asphyxiants. So they've got a few nasties in there, so be aware of that. Over recent years, and it's ongoing, many refrigerants have been phased out or are in the process of being phased out due to their components, chemical composition. CFCs were phased out many years ago, but HFCs now are on the way out and so on. And new refrigerants are being developed continuously in the search for increased energy efficiency, reduced environmental impact, and reduced toxicity and so on. As I said, you can find a lot of information online. Generally, the ones that you'll come across, R22, that's being phased out. That used to be the standard refrigerant for DX split systems. But it's still available, and there are still some units running on R22, but they won't be replaced with R22. So now, for the smaller systems, it'll be either 410A, you'll see that, or R32. 410A has got a higher GWP, global warming potential, than R32. So there's still some units being manufactured with R410A, but it will be phased out, and R32 will take over. R123 is mainly used in large centrifugal chillers, Trane in particular. Last time I worked on a Trane chiller, it was R123. That may have changed. Things keep changing all the time, so you need to be aware of what the refrigerants are. It's in the process of being phased out by 2030. So they've got to work up something new. I'll jump down to this one, R1234YF. I don't know whether you've come across that. That's being used in centrifugal chillers, particularly the turbo core type compressors. It's got a global warming potential less than 1. Its thermal performance is lower than other refrigerants used in chillers. So it tends to make the chiller bigger to get the same capacity. But the environmental benefits are making it a more popular choice. So R134A, that's still around, but it's being phased out. It's been in the process of being phased out since 2012 due to its high global warming potential. It's still used, I think, in hydronic heat pumps and chillers, but it will be phased out. There are some natural refrigerants as well, ammonia. Just have a drink. It's commonly used in industrial refrigeration systems. Got low global warming potential, high energy efficiency, system flexibility, and low cost, but highly toxic and corrosive. So you may have come across this. It's used in things like meatworks, dairies, where it's a distributed system, and instead of using chilled water, because they need lower temperatures as well, ammonia is good because you can pump it around a campus in a similar way to what you can pump water. But if you have a leak, I guess you've all smelled ammonia. It's pretty bad stuff to smell. And if you have a major leak, you've got a big problem. But it is still used, and it's really flexible, and it's a good option for those sort of situations. Also, carbon dioxide is being used occasionally. It has been used in chillers. It's used more in industrial refrigeration, but there are some chillers available using CO2, and it may become more popular as time goes on. It's non-toxic, non-flammable, but isn't asphyxiant. And CO2, obviously, if there's a leak, you're putting more CO2 into the atmosphere. So it's CO2 is often also used as a fire retardant. It used to be used in computer rooms. If there was a fire alarm, they'd release carbon dioxide to try and stop the flames. Basically removes the oxygen from the air, displaces the oxygen. But if there's anyone in the room, they can't breathe, so it's potentially dangerous. All right, well, I've gone through that very quickly, but hopefully it's been of some benefit to you. You've got some notes, and you can look back on the video if you want more information, or just contact me if you want to have a chat about anything at all. Any questions? I'll rush through it a bit to get through on time, but no questions? All good? Okay. Thank you. We'll see you next week.
Thanks for that.
Thanks, guys.